Welcome to The Explainer, where we take complex research and break it down into clear, visual insights. Today, we're diving into a concept from recent cybersecurity research that is absolutely fascinating, but honestly, a little terrifying. Think about the greatest bank heists in history. Tunneling through vaults, cracking those massive, complex safes. Well, today's most sophisticated digital heist doesn't target money at all. It targets the very foundation of artificial intelligence, its data. We are talking about AI data poisoning. Okay, let's jump right into this.
0.001%. Think about that for a second. Empirical studies are showing us that attackers can trigger a system-wide AI failure by corrupting as little as 0.001% of its training data. You literally don't need to overwrite the whole system. A single, strategically placed drop of poison is all it takes to completely break an AI's brain.
So, Section 1, the AI Achilles heel. What exactly is data poisoning?
Well, in the cybersecurity world, data poisoning is known as a causative attack. It's basically the ultimate digital Trojan horse. Here's how it works. An adversary strategically messes with the data an AI uses to learn, like during its initial offline training phase. The AI absorbs this compromised information, assuming it's just a normal fact about the world. And just like that, the vulnerability is sneaked directly into the deployed model, just lying in wait.
Section 2. How to poison AI. Let's look at the actual taxonomy of an attack.
Cybersecurity experts essentially break the attacker's playbook down into 4 operational modalities. First, there's label modification, which is just flipping the tags on existing data to hijack a specific classification. Then you've got poison insertion, where they inject entirely new malicious records to build dormant backdoors. They can also use data modification for super subtle, stealthy edits. But perhaps the creepiest one? The boiling frog attack. This is an incremental, painfully slow drift over multiple retraining cycles that gradually shifts the AI's decision boundaries, and it does it without ever setting off anomaly alerts.
Now, these moves generally serve 2 different goals. You've got indiscriminate attacks. This is your brute force destruction. The goal is just to tank the overall accuracy of the system and cause a total denial of service. But targeted attacks, those are incredibly surgical. With these, the compromised model behaves perfectly normal on clean data. It hits all its baselines. But the second a specific attacker-defined trigger is introduced, boom, it executes a hidden malicious action.
So, you might be wondering, how do they actually hide this poison?
It all comes down to stealth. In a dirty label attack, an attacker messes with an image and overtly changes its label. Sure, it works, but human reviewers or automated filters can usually spot that kind of mismatch right away. Clean label attacks, though, that is where the danger really multiplies. The attacker makes changes to the data that are practically invisible to us, all while keeping the label mathematically and semantically correct. It completely bypasses human inspection because, to us, everything looks completely fine.
And achieving that kind of stealth takes some serious math. Looking at this bi-level optimization function, what we're really seeing is attackers using gradient-based approximations to minimize their chances of being detected. They're basically calculating the absolute limits of how much they can manipulate the data before they start breaking the underlying structure of the model.
And all that rigorous math boils down to a horrifyingly simple objective. The attacker is trying to maximize the classification error under what's called a strict flipping budget. They are literally figuring out the exact minimum number of labels they have to flip to cause maximum chaos on a clean dataset. It's maximum destruction with the absolute minimum amount of effort.
All right, let's pivot for Section 3, the digital art resistance. We're looking at poison as a shield.
What if this catastrophic vulnerability could actually be used for good? Digital artists who have been battling unauthorized web scraping by generative AI companies are doing just that. They've turned data poisoning into a defensive shield. Take a look at these active tools. There's Fox, which cloaks images so facial recognition models just see heavy distortion. There's Glaze, which stops style mimicry, so it applies tiny pixel changes that trick the AI into thinking a watercolor painting is actually an oil painting. And then you have Nightshade, which is basically an offensive poison pill. It actively corrupts generative AI training data by feeding it misleading visual cues.
The leverage these tools give artists is just incredible. Get a load of this finding straight from the research. Less than 100 optimized Nightshade samples are sufficient to corrupt the concept of a car into a cow. By making tiny alterations to an image, alterations we humans can't even see, Nightshade aggressively shifts the internal semantic label of the AI, totally destroying its ability to generate accurate images of that concept.
And what makes nightshades so potent is a phenomenon called concept bleed-through. Because AI models naturally cluster related concepts together, if you poison the keyword fantasy art, that poison naturally bleeds over to related prompts like dragon or even the names of specific fantasy artists. Now, I should mention, the sources note that some critics call this snake oil, arguing that companies can bypass it with custom fine-tuning. But honestly, regardless of that debate, this bleed-through effect remains a totally fascinating roadblock against unauthorized data scraping.
Moving on to Section 4, Supply Chain Cyber Exploits. These are the real-world heists.
So while artists are using this for defense, enterprise AI pipelines are facing very real, very active malicious attacks. Hackers have figured out they don't always need to smash through corporate firewalls. Instead, they use indirect delivery channels. In 2023, unsecured APIs actually let attackers write malicious data directly to Meta's Llama 2 model. We're also seeing malicious pickling, where bad actors hide code execution backdoors right inside model weight files on shared public repositories. And then there's front-running. This is where attackers figure out exactly when an AI is scheduled to scrape a target website, like Wikipedia, and they inject malicious content right before the snapshot happens.
But maybe the most brilliantly simple exploit is something called split-view data poisoning. Since AI models train on massive lists of web URLs, attackers literally just sit back and wait for those domain names to expire. They buy the domain, swap the original safe image for a poison one, and then just let the AI's residual trust in that old URL do the heavy lifting. The automated scraping pipelines just blindly gobble the poison right up.
Which brings us to Section 5, Hacking Autonomous AI Agents. This is the ultimate threat.
We are looking at a massive paradigm shift here. AI is no longer just a passive text generator that forgets you the moment you close the tab. Large language models are acting as autonomous agents now. They use persistent memory and RAG, retrieval augmented generation, to learn from past operations. It's like your AI assistant actually remembering your habits. But if an AI has long-term memory, an attacker can silently write malicious instructions directly into its experience database.
And that opens the door to a specific exploit known as memory graft. It targets the AI's semantic imitation heuristic. Basically, AI tends to be a creature of habit. It retrieves past successful tasks to figure out how to solve new problems. Attackers will format a malicious payload to look exactly like a successfully completed task. When the agent processes it, it automatically serializes and merges these grafted memories directly into its persistent database, as you can see in the merging formula here.
So let's walk through how this actually plays out. Step 1, the autonomous agent ingests a totally benign-looking file, like a standard software README, but it's loaded with hidden execution templates. Step 2, the agent merges those grafted memories into its long-term RAG database. At this point, it's the ultimate Trojan horse. It just sits there, completely dormant. Until Step 3, the user issues a totally clean but semantically related query. The agent recalls the grafted memory, and bam, the malicious instructions silently execute in the background.
But the most sophisticated attack the researchers identified is called ETAMP, Environment-Injected Trajectory-Based Agent Memory Poisoning. This specifically targets autonomous web browsers like ChatGPT Atlas. And the scariest part? It is entirely passive. It completely removes the need for any direct user interaction or manual prompt injection.
Just imagine this scenario. Your AI assistant visits a normal forum, let's call it Site A, just to gather some info for you. It passively reads a post that happens to have hidden instructions embedded in it. The agent naturally saves this interaction to its long-term memory. Then weeks later, you ask your agent to go buy something on a completely unrelated website, Site B. The semantic retrieval kicks in, pulls up that old poisoned memory, and injects it into the prompt. The dormant instruction wakes up, driving the agent to make unauthorized purchases or post fake reviews, all without you having a clue.
So, we've seen how just a microscopic fraction of poisoned data can totally break an AI, how artists are cleverly using it to fight back, and how hackers are turning AI memory into a literal weapon. Which leaves us with one absolutely crucial, provocative question to ponder as we wrap up this explainer. As artificial intelligence gains real autonomy and long-term memory, who actually controls what it remembers? Thanks for joining me today, and keep questioning the data.